Welcome to the Deep Dive, where we take your dense sources and carve out the core knowledge. Today's mission is, well, it's arguably the most ambitious we have ever undertaken. We're plunging into a document that sits right at the frontier of advanced number theory and algebraic geometry.
It's a fascinating one. Our source is the paper on the Outer Automorphism Groups of the Absolute Galois Groups of Two-Adic Local Fields by Yu Nishio, dated December 2025. And this deep dive is really all about understanding the fundamental symmetries of number systems, specifically the structure of the two-adic fields, which, we'll just call K for short.
The technical request from the listener for this was for extreme thoroughness, and we are absolutely going to deliver on that. We're entering the world of p-adic numbers, but we're focusing on the really tricky case where the prime p is equal to 2. Our goal is to measure the difference between the field's intrinsic symmetries and its more abstract algebraic symmetries.
And that takes us immediately into the heart of something called anabelian geometry. So we start with a two-adic local field, K. You can think of this as a finite extension of the base field Q sub 2, the field of two-adic numbers. These fields are what's called mixed characteristic. I mean, the field itself has characteristic 0, but its residue arithmetic operates in characteristic 2. And this mix is really what brings in all the complexity.
And the algebraic objects we're looking at are they're huge. We have the absolute Galois group, G sub k, which is this massive group that encodes all possible algebraic extensions of our field K.
That's right. G sub k is a large, very complex topological object. It's what's known as a profinite group. And this study focuses on its symmetries, the outer automorphism group, or out of G sub k. These are the abstract symmetries of the group structure itself, completely divorced from simple field operations. So the core question of the whole paper is how much larger and, frankly, how much wilder is out of G sub k than the group of simple field symmetries, which we call out of K.
Okay, let's unpack this paper, and we have to start with the abstract. It really sets the entire stage.
So the author, Yu Nishio, begins by framing the work through the lens of anabelian geometry. This is it's a profound concept. It originates with Alexander Grothendieck back in the 1980s.
We absolutely have to dedicate some time to defining anabelian geometry properly. What is the grand vision here?
Anabelian geometry, it fundamentally flips the script on traditional algebra. I mean, normally you define an algebraic object, like a field K, and then you derive its fundamental group G sub K. Anabelian geometry asks if you can do the reverse. Can you reconstruct the field K, or maybe a geometric curve, purely from the knowledge of its non-abelian fundamental group, G sub K?
And if you can perfectly reconstruct the object just from its group, then that object is called anabelian.
Precisely. In that kind of perfect world, the field symmetries, out of K, would align perfectly with the group's abstract symmetries, out of G sub K. They'd be the same thing. But for most fields, this just isn't true. And p-adic fields are a classic example of not anabelian objects. So the study becomes about quantifying that failure, especially for the historically difficult p equals 2 case.
So just to summarize the framework from that very first sentence of the abstract, Nishio is studying the abstract symmetries of two-adic local fields to basically gauge the size of the gap between the algebraic symmetry and the field symmetry.
Yeah, that covers the initial setup. We've defined the objects, the theoretical framework.
Okay, that feels complete for the first sentence. Have we missed any nuances about the anabelian setup here?
No, I think we've thoroughly unpacked it. We've focused on Q sub 2 and the basic role of out of G sub K. Let's proceed to the background results mentioned in the next paragraph.
Right. The second sentence of the abstract recalls a fundamental relationship. It's about how the field automorphisms relate to these outer automorphisms.
And it's a well-known result. There's a natural homomorphism, a map, from the field automorphism group out of K to the outer automorphism group out of G sub K. And crucially, this map is injective.
Why is that injectivity so critical? What does it let us do?
It means we can embed out of K as a subgroup inside the much, much larger out of G sub K. You can think of out of K as consisting of the tame symmetries. They're finite, they're field-preserving actions. And we regard out of G sub K as the whole universe of abstract symmetries that G sub K possesses. So what we're really looking for are the elements in out of G sub K that are not in out of K, the wild ones.
The abstract then references prior results from Nishio and Hoshi, but for odd primes p, they found that for certain absolutely abelian mixed characteristic local fields, the subgroup out of K is not normal in out of G sub K and has infinitely many distinct conjugates.
Yeah, and this prior result sets a really high bar. I mean, a subgroup is normal if it's stable under conjugation. It stays put. Non-normality means an element, let's call it alpha, in out of G sub k can transform out of k into a completely different, though isomorphic, subgroup out of k prime. And if there are infinitely many distinct conjugates, well, that implies extreme structural chaos. It means out of G sub k is infinitely large, and it violently destabilizes out of k.
We should probably quickly define absolutely abelian here, just to be precise.
Good idea. An absolutely abelian field K over Q sub P, it simply means that the field extension itself is Galois, and the field Galois group, gal of K over Q sub P, is commutative or abelian. This condition is really just imposed to simplify the group structure enough to make the wild inertia manageable. But the overall absolute Galois group, G sub K, remains fiercely non-abelian.
Okay, so now for the core challenge this paper addresses. Moving from odd P to P equals 2. The first main result stated in the abstract is to extend this chaos to two adic fields.
Right. The paper asserts that if a two-adic local field satisfies certain conditions, then the set of conjugates of out of K in out of G sub K is infinite, and that confirms the non-normality. This is a significant leap because the algebra for P equals 2 is just notoriously messy.
Why is P equals 2 so much harder? What's the fundamental obstacle?
It really comes down to the structure of the units, particularly the torsion. For odd primes, the p-adic units are, well, they're simpler. They behave nicely under the p-adic logarithm. For p equals 2, the presence of the primitive fourth root of unity, I, which satisfies I squared equals minus 1, introduces this tricky 2 torsion that doesn't simplify cleanly with the standard logarithm techniques. So Nishio has to navigate all of this complexity.
Okay, so that completes the discussion on the non-normality and infinite conjugates result, covering the prior work and the paper's first main assertion. Have we missed any nuances regarding that complexity jump from odd P to P equals 2?
I think we've thoroughly unpacked it. We've emphasized that P equals 2 introduces these unique algebraic complexities that the paper has to overcome. So let's proceed to the second main result, which is about representations.
Right. The abstract now pivots to p-adic Galois representations, linking this structural chaos we've been talking about to geometric stability.
And again, it starts with prior work. Hoshi's work for odd primes P showed that a p-adic Galois representation could start out nice, specifically Hodge-Tate, but then conjugation by one of these outer automorphisms would just destroy that property.
Okay, let's break that down. A p-adic representation, P is basically a map from our abstract Galois group G sub K to concrete linear transformations on a vector space V. And Hodge-Tate it's a marker of desirable geometric structure, right?
Exactly. Hodge-Tate representations are considered well-behaved in p-adic Hodge theory. They connect the Galois actions to linear algebra in a way that respects certain deep algebraic filtrations. Hoshi showed that these abstract symmetries in out of G sub K can destabilize these fundamental geometric properties.
And so, main result 2 in this paper is the P equals 2 analog. Nishio proves the existence of a similar pair, a representation rouleau and an automorphism alpha, such that alpha disrupts the Hodge-Tate property.
This is a crucial validation. It means the wild nature of out of G sub K isn't just structurally chaotic, it's also geometrically disruptive. And this disruption holds even for the complicated dyadic P equals 2 field structure.
The abstract closes with a list of keywords, and one of them is ought-intrinsically Hodge-Tate. We saw that this term implies stability.
Yeah, ought-intrinsically Hodge-Tate means a representation is stable under all possible Galois group automorphisms. If a representation satisfies this, it's completely immune to the chaos we've been discussing. Nishio's work proves the existence of a representation that is initially crystalline, which is a very strong desirable property that implies Hodge-Tate, but is not ought-intrinsically Hodge-Tate. And why not? Because the automorphism alpha breaks it.
So that concludes the abstract, covering the key results about the Hodge-Tate disruption for P equals 2. Have we missed any nuances regarding the definition of ought-intrinsically Hodge-Tate?
I think we've thoroughly unpacked it, just noting that the paper demonstrates this instability. So with that, let's move to the introduction on page 2.
The introduction starts by reiterating the definitions of G sub K and out of G sub K, and it confirms that injective embedding of out of K into out of G sub K.
Right, and what's most important here is really understanding the context of the size difference. You have to remember, out of K is finite. It represents the very limited symmetries of the field extension itself. And when P is odd, we already knew that out of K is strictly smaller than out of G sub K. So this excess of abstract automorphisms, the elements in out of G sub K that do not come from the field K, that's what makes these fields not anabelian.
So the whole point of the paper is trying to quantify the size and the behavior of this difference.
Yes. That gap is the whole problem. Out of G sub k contains symmetries that arise purely from the topological and group theoretic structure of G sub k, and these are symmetries that are completely invisible if you only look at the arithmetic of the field K.
Okay, that establishes the context, defining the difference between out of K and out of G sub K as the central interest. Have we missed any nuances regarding that historical non-anabelian conclusion?
I think we've thoroughly unpacked it. The key is that prior work really focused on P being odd. Now we can proceed to the new challenge.
So why was the P equals 2 case left as a known gap for so long before this paper?
Well, historically, P equals 2 is just much more algebraically challenging. For instance, the machinery of the p-adic logarithm, which is crucial for linking the multiplicative unit structure to the additive vector space structure, it just breaks down in a non-trivial way at P equals 2. This requires completely new technical tools to even begin the construction of this disruptive automorphism alpha.
And the paper addresses this gap. It says, the present paper gives a certain answer to this question.
Right, and now we get to how Nishio overcomes this. The author introduces the core technical tool used throughout the paper.
The authors introduce the field K, but viewed solely as an additive module, which they write as K+, and they discuss the reconstruction algorithm.
And this is the operational core of the entire paper. Monoanabelian geometry provides a functorial reconstruction algorithm that lets us recover the additive structure K+ purely from the group G sub K. Crucially, this allows us to define an action of the entire outer automorphism group out of G sub K on the vector space K+.
And why is this action so important? What does it unlock?
It lets us translate abstract group symmetry into concrete linear algebra. Any alpha in out of G sub K induces a linear map, which the paper calls alpha plus, on K+. Now, if alpha happens to be a tame field automorphism, then alpha plus is a tame linear map. We are looking for an alpha whose induced linear map alpha plus is wild.
And the ultimate test of wildness is base field preservation. The vector space K+ is a vector space over Q sub 2. A tame field automorphism has to fix Q sub 2 element-wise.
Exactly. So if we can find an alpha in out of G sub K whose linear action alpha plus shifts or moves the additive structure of Q sub 2, we've proven that alpha is truly a new non-field derived symmetry.
Okay, so that covers the motivation for studying P equals 2 and the key technical tool, this action of out of G sub K on the additive structure K+. Have we missed any nuances regarding the significance of this action? The fact that it coincides with the out of K action only on the restriction.
I think we've thoroughly unpacked it. The restriction coinciding just means the field automorphisms are tame on K+, as we expect. We are looking for elements in out of G sub K that are wild. And so let's look at theorem A, which finds one.
Right, theorem A, which is later formalized as theorem 2.5, identifies the specific conditions necessary for this chaos to occur and proves the existence of this wild element, alpha.
And the conditions are, 1, the field K must contain a primitive fourth root of unity, let's just call it I, and 2, the extension K over Q sub 2 must be Galois and abelian.
So condition 1 containing I, that's the key P equals 2 requirement.
Yes. It introduces essential two torsion into the multiplicative group of units, which is necessary for the subsequent algebraic construction using group generators to work. Without I, the algebra is actually too simple. And condition 2, that just simplifies the field Galois group gal of K over Q sub 2, so that the non-abelian wild inertia, which is the actual source of the complexity, is structured enough to be analyzed.
Now, for the assertion of theorem A, it says there exists an outer automorphism, alpha, of G sub K, such that for any power, alpha to the n, the induced action alpha to the n plus, fails to preserve the base module Q2 plus. So alpha n plus of Q2 plus is not equal to Q2 plus.
This is the fundamental result. And the why here is that this violation immediately proves that alpha cannot be a field automorphism, because field automorphisms must fix Q sub 2. Furthermore, the fact that this holds for every non-zero integer n means we have infinitely many distinct wild automorphisms, alpha, alpha squared, alpha cubed, and so on. This proves that the size of this excess group is infinite.
The brilliance here seems to be constructing one specific mathematically controllable element, alpha, whose existence is enough to trigger infinite chaos throughout the entire structure.
Precisely. That's the whole game.
Okay, so that covers theorem A, establishing the existence of a non-trivial automorphism alpha that fails to preserve the underlying Q sub 2 additive module. Have we missed any nuances on why preserving the Q sub 2 structure is so necessary for a field automorphism?
I think we've thoroughly unpacked it. Fixing Q sub 2 is just axiomatic for field automorphisms. Alpha violates this. So now let's look at the subsequent theorems that are built on this existence.
Right, so theorem B, which is formalized later as 3.2, takes the existence of alpha and converts it into the non-normality result. The set of out of G sub K conjugates of the subgroup out of K is infinite.
And this is the structural chaos conclusion. Since the alpha to the hen are non-field preserving, by theorem A, they can't normalize out of K. And because we have infinitely many such elements, the normalizer of out of K must have infinite index in out of G sub K. This leads to infinitely many distinct conjugate subgroups that are all isomorphic to out of K. So out of K is just extremely unstable within the larger group structure.
And theorem C just formalizes this. Out of K is not normal, and there are infinitely many distinct subgroups isomorphic to out of K.
Yes, this fully answers the paper's central question about quantifying the difference. The difference is infinite, and it breeds instability.
And finally, theorem D, which is corollary 4.5, the geometric consequence. There exists a representation, Avogadro, that is irreducible, abelian, crystalline, and therefore Hodge-Tate, but it's not intrinsically Hodge-Tate.
And this links the structural result back to p-adic geometry. We find a representation that is as nice and geometrically sensible as possible. I mean, crystalline representations are highly desired by mathematicians, but the abstract group symmetry alpha still possesses the power to shatter that geometric stability. The composition row circle alpha is no longer Hodge-Tate.
It's just fascinating how this one element, alpha, drives all three of the major conclusions. Its existence in theorem A, the infinite structural chaos it creates in theorems B and C, and the geometric destruction it causes in theorem D.
It's a completely cohesive argument and built entirely on the construction of that single, specific, unipotent automorphism.
Okay, so that concludes the main results, showing how this non-field-like automorphism alpha leads to both infinite instability and the instability of the crystalline representation Rho. Have we missed any nuances regarding how these two results relate?
I think we've thoroughly unpacked it. There are both consequences of out of G sub K containing these strange group theoretic symmetries that just cannot be explained by the field structure alone. Let's proceed to the notational conventions.
Right. Section 0 of the paper is about notational conventions, and the request was for extreme granularity, so we have to go through this line by line. First up, topological groups.
So if G is a topological group, the paper writes G superscript ab for the abelianization of G. This is the quotient by the commutator subgroup. It just simplifies the structure. Then you have G abtor, which is the closure of the subgroup of torsion elements of G ab. And then G abtor is the quotient of G ab by G abtor. This is about removing elements of finite order to study the free component of the abelian group.
And then for a profinite group H and a prime P, it writes H superscript P.
Right. HP is the maximal pro-P quotient of H. This is about focusing strictly on the primary parts of the group, which is absolutely necessary for p-adic theory. And a profinite group itself, we should mention, is an inverse limit of finite groups. It's the essential structure for our Galois group G sub K.
And then the conventions for rings, R plus for the additive module, and R cross for the multiplicative group of units. Pretty standard stuff.
Yes.
Okay, that covers the various structures derived from topological groups and rings. Have we missed any nuances on the role of HP in isolating the key behavior?
I think we've thoroughly unpacked it. HP is crucial for focusing on the p-adic specific torsion in our case. Let's proceed.
Next heading, modules. M hat is defined as the projective limit of M modulo n times M.
Right. M hat is the perfinite completion.
Then fields. It defines a mixed characteristic local field as a field isomorphic to a finite extension of Q sub P, and then a whole list of invariants for mixed characteristic local field K.
Let's go through them. K sub D1 is the minimal mixed characteristic local field inside K. A sub K is the absolute residue degree. D sub K is the degree of the finite extension K over this minimal field K sub D1. O sub K is the ring of integers of K. M sub K is the maximal ideal of O sub K.
And then O pre-K, which is defined as 1 plus the maximal ideal M sub K. This is a subgroup of the units.
Yes, and this is an important one, O pre-K, the 1 units. They are the elements of the multiplicative group that are closest to 1, and their structure is intimately tied to the wild inertia of G sub K. They're key.
Right. And then P sub K is the residue characteristic. And a sub K is the largest non-negative integer such that K contains a primitive P sub K to the A sub Kth root of unity.
And a sub K is what determines if the field contains I. For our hypothesis later on, we'll need a sub K to be greater than or equal to 2 for P equals 2.
And the final notational point is that a group isomorphic to the absolute Galois group of one of these fields is called a group of MLF type.
Yes, mixed local field type.
Okay, that covers the comprehensive list of fields and variants, including the 1 units oprec and a sub k. Have we missed any nuances regarding the link between d sub k and the extension k over k sub d1?
I think we've thoroughly unpacked it. D sub k is the relative dimension, and we'll see later that this relates directly to the dimension of the Q sub 2 vector space K+. Let's jump into section 1.
So, section 1, construction of the unipotent automorphism alpha star. The goal here is to prove that a group of MLF type admits an automorphism that satisfies a certain unipotency condition.
Right, so we start with an abstract group G of MLF type. And by applying all these functorial group theoretic reconstruction algorithms, we obtain a list of invariants. We can recover P of G, D of G, F of G, A of G, the wild inertia subgroup P of G, and the topological modules K plus of G and oprec of G.
And the paper then confirms on page 5 that these abstractly reconstructed group structures are isomorphic to the concrete field structures. So P of G sub k is P sub k, D of G sub k is D sub k, and so on.
Yes, the reconstruction works perfectly. There are functorial isomorphisms, and it's important to re-emphasize the definition of K plus of G. It is defined as oprec of G, tensored with the rational numbers Q. It's a rational vector space derived directly from the wild inertia elements.
So the additive structure of the field comes from the wildest part of the Galois group.
Exactly, and for this section, the paper imposes the crucial assumptions. P of G equals 2, and A of G is greater than or equal to 2.
So we're in the p-adic world, and our field contains that primitive fourth root of unity.
That's the meta.
Okay, that covers the reconstruction of the field invariants from the abstract group G and confirms the core assumptions. Have we missed any nuances regarding the connection between P of G and oprec of G?
I think we've thoroughly unpacked it. P of G is the non-abelian wild inertia, and oprec of G captures its abelian component, which is critical for defining the vector space K plus of G. Let's proceed to Descartes' proposition.
Proposition 1.1 from Descartes. This gives us the topological generators and relations of G.
Yes, there are topological generators, sigma tau, and then x naught up to xd of G. Sigma is the Frobenius, tau is the tame inertia, and the x sub i's are the wild inertia generators. They're the ones that generate the normal closed subgroup P of G.
The second relation is sigma tau, sigma inverse equals tau to the power q of G, where q of G is 2 to the f of G.
A standard relation. This defines the group structure outside the wild inertia.
But the third relation is the complicated one. It dictates how the Frobenius acts on the first wild inertia generator. It says sigma x naught sigma inverse is equal to a very complex expression involving powers and commutators of the other x sub i's.
This complex relation is the key input. It dictates the entire topological and algebraic structure of the wild inertia. And this is essential for determining which of these generators are actually independent when we move to the vector space K plus of G.
Okay, that covers the precise topological presentation of G, including the 3 fundamental relations from Descartes' work. Have we missed any nuances regarding the nature of the coefficients, like PG in that exponent?
I think we've thoroughly unpacked it, stressing that these relations are nonlinear and they define the non-abelian complexity of G. Let's now proceed to the linear structure of K plus of G.
So we write S for the set of indices 0 to D of G. And for each index I, we write Y sub I for the image of the generator X sub I in the vector space K plus of G.
Right, and lemma 1.2 confirms that K plus of G has a natural structure of a Q sub 2 vector space, and its dimension is D of G.
The same as the field extension degree. Now, lemma 1.3 states that the D of G elements Y1 through YD of G form a basis of this vector space.
Yes, and this is the crucial algebraic consequence of that complex relation from Descartes.
The why here is, why is U naught missing from the basis?
Because that highly complex group relation implies that the group element x naught is dependent on the others when you pass to the abelianized torsion-free quotient. This means its image I naught is not required for the basis of K plus of G. The space is spanned entirely by Y1 up through ID of G.
And lemma 1.4 is a small but necessary check. It confirms that the element Y sub D of G minus 1 is a non-zero element of K plus of G.
Yes, it's critical because it's part of the basis, so it has to be non-zero. And it's the element we're about to use to define the shear transformation.
Okay, that covers the dimension and basis of the Q sub 2 vector space K plus of G, relying on the constraint imposed by the group relations to eliminate E naught. Have we missed any nuances on the non-zero status of Y sub D of G minus 1?
I think we've thoroughly unpacked it. The basis U1 through YD of G is the coordinate system for our linear analysis. Let's define the shear automorphism.
Definition 1.5. We shall write alpha star for the automorphism of G, defined by.
Okay.
Well, it's the identity on sigma and tau, and it's the identity on all the x sub I generators except for the very last one, x sub d of G, that changes alpha star of xd of G is equal to xd of G minus 1.
So this is a very specific controlled perturbation. It's a multiplicative shift at the group level. And when you translate this to the additive module k plus of G, this becomes a simple linear shear. The basis vector y sub d of G maps to yd of G plus yd of G minus 1. All the other basis vectors, y sub I for I less than d of G, are fixed.
It's the simplest possible non-trivial change you could make, really.
It is, and theorem 1.6 proves the properties of this change. It says for any non-zero integer n, if you write alpha n star plus for the automorphism induced on the vector space, then this map is not the identity, and moreover the equality. The quantity alpha n star plus minus the identity squared is equal to 0.
And this condition, t minus I squared equals 0, defines what's called a unipotent linear operator. It's a shear matrix. It means the automorphism is close to the identity, but distinctly not the identity.
Right. And the proof of that non-triviality is elegant. The induced action on yd of G is yd of G maps to yd of G plus n times yd of G minus 1. So if this map were the identity, it would mean that n times yd of G minus 1 is 0, but that contradicts lemma 1.4, which said that basis vector was non-zero.
So the contradiction proves it. Okay, so that covers the full construction and algebraic proof of the unipotent automorphism alpha star acting on k plus of G. Have we missed any nuances regarding how the power n distinguishes the different alpha?
I think we thoroughly unpacked it. The integer n means we have infinitely many distinct automorphisms, alpha to the n. Now let's look at the corollaries on page 7.
Corollary 1.7 draws the immediate consequences. The image of the homomorphism from the outer automorphism group to the automorphism group of k plus of G is infinite.
Yes.
And the outer automorphism group of G is infinite.
Yes, it's a logical cascade. We have infinitely many distinct powers of alpha star. They all act non-trivially on k plus, which implies that the group they came from, out of G, must be infinite. This is the first major structural finding for the p equals 2 case.
And remark 1.8 then acts as a sanity check. It recalls that if d of G is equal to 1, this whole thing is trivial.
Right, if the field is just q sub 2, there's no complexity. The result requires d of G to be at least 2. You need that non-trivial wild inertia generated by those x sub i's to get the whole machine working.
Right, so that concludes section 1. We've established that out of G sub k is infinite when d of G is at least 2 and p equals 2. Have we missed any final nuances on the structural necessity of d of G being greater than 1?
I think we've thoroughly unpacked it. This infinite structure is entirely dependent on the existence of that non-trivial wild inertia. So let's proceed to section 2, where we apply this abstract thing to the actual field structure.
Section 2. Applying alpha star to the field structure.
Sure.
The goal here is to prove that the absolute Galois group of a certain two-adic local field admits an automorphism that has an interesting property.
Yes, and that interesting property is that it's not field preserving. So definition 2.1 formalizes the terms. We say an automorphism alpha of k plus is QPK plus characteristic if it maps the base field's additive structure to itself as a set. And we say it's QK plus preserving if it does that, and it's the identity on the base field. It fixes every element. A true field automorphism must be QPK plus preserving. We're going to use this to detect our non-field-like automorphism.
So this is the crucial test. The non-field-like behavior has to be detectable in how it acts on Q sub 2.
Exactly. If alpha star preserves Q sub 2, it could potentially be a field automorphism. If it moved Q sub 2, it absolutely cannot be.
Okay, so that covers the crucial definitions of characteristic and preserving actions on the base field Q sub 2. Have we missed any nuances regarding the difference between characteristic and preserving?
I think we've thoroughly unpacked it. Characteristic just means the set is mapped to itself. Preserving means every single element is fixed. Let's proceed to lemma 2.2, which introduces the necessary algebraic constraints.
Lemma 2.2. This introduces fundamental algebraic constraints. It says any Galois group automorphism alpha must respect the trace and norm maps relating the field K to its base field.
Yes. The most critical consequence here from part 2 of the lemma is that the induced additive action alpha plus must preserve the kernel of the trace map. The trace map sums conjugates of an element. Its kernel is the subspace of elements that average to 0 under the Galois group action. This subspace is a fixed, invariant structure defined by the field extension itself.
So we have two forces at play. We have the unipendency property, t minus I squared equals 0, and we have this requirement that alpha plus must leave the trace kernel invariant. And Nishio is going to use the clash between these two properties to prove a contradiction.
It's beautiful. It's mathematical jujitsu. The extremely simple nature of the shear alpha plus makes it easy to analyze, while the trace map provides this rigid constraint that cannot be violated by any legitimate Galois automorphism.
That covers the fundamental constraints imposed on out of G sub k by the trace and norm maps. Have we missed any nuances regarding how the trace kernel relates to the field extension?
I think we've thoroughly unpacked it. The trace kernel consists of elements that average to 0, and this space must be invariant under alpha. Let's proceed to the contradiction proof.
Lemma 2.3. This proves a contradiction for the simplest case, where d sub k equals 2 and k is just q sub 2 with I8 adjoined. It asserts that the automorphism alpha star we defined is not q2 plus characteristic. It moves the base field structure.
Right. So we assume, for the sake of contradiction, that alpha n star plus is q2 plus characteristic. In this quadratic extension, the vector space k plus is spanned by the basis elements 1 and I. Since we're assuming it's characteristic, the element 1 must map to some element b in q sub 2. And then the trace kernel constraint forces I to map to c times I for some other c in q sub 2.
And now the unipotency property comes in. The authors apply the relation t minus I squared equals 0 to a general element x plus yi.
Right. And when you apply the square of the difference, the calculation yields 0. Since 1 and I are linearly independent, this equation forces the coefficients to be 0. You get b minus 1 squared equals 0 and c minus 1 squared equals 0.
Which means b must be 1 and c must be 1. This implies that alpha n star plus must be the identity map on the bases 1 and I.
If it's the identity map, it means alpha to the n is trivial. But we proved back in theorem 1.6 that alpha to the n is not trivial. This is a contradiction. And it proves that our initial assumption that alpha to the n is q2 plus characteristic must be false.
That is powerful. The unipotent shear, which was designed to be the simplest possible non-trivial action, cannot simultaneously satisfy the field's extension constraints from the trace map and the non-triviality required by the group structure, unless it acts wildly on the base field q sub 2.
That's it. That's the core of the argument.
Okay, that covers the crucial contradiction proof. It links the unipotency property to the trace map constraints and concludes that alpha star has to move the q sub 2 base field. Have we missed any nuances on why that unipotency relation is so constraining?
I think we've thoroughly unpacked it. The unipotency restricts the transformation to a simple, non-diagonalizable shear. If a shear fixes the basis, it must be trivial. But alpha star is designed to be non-trivial. Now let's look at the generalization steps.
Lemma 2.4 then generalizes this result from the simple dk equals 2 case to any absolutely abelian field k that satisfies the conditions.
Yes, and this is an essential step. It proves that this wildness is preserved under restriction. If an automorphism alpha prime moves the base field in a simpler field k prime, then its restricted action alpha must also move the base field in the more complex field k.
And this leads to the final formal statement of Theorem 2.5, which is what the paper labels Theorem A in the introduction. It confirms the existence of a non-Q2 preserving automorphism alpha in out of G sub k for these general two-adic fields.
Yes, the entire construction is now verified. We've built our source of chaos, alpha, and we have proved that it is distinct from any field symmetry in out of k. So now we can use this element to prove the infinite instability formally.
Okay, that completes section 2 and the proof of Theorem 2.5. We have our non-Q2 preserving automorphism alpha. Have we missed any nuances on the overall constructive logic?
I think we've thoroughly unpacked it. The construction is solid. It goes from group relations to linear algebra to a field theory contradiction. Let's proceed to section 3 and the non-normality.
Right, section 3, non-normality and infinite conjugacy. This connects the technical result we just proved, the non-Q2 preservation, directly back to the group theoretic consequence of non-normality. And this is done through Lemma 3.1.
Lemma 3.1 is the strategic bridge. It states, if an automorphism alpha normalizes the field automorphism group out of K, then alpha must be QPK plus preserving.
So if we invert that logic, if an element alpha is not QPK plus preserving, which we just proved for our alpha to the n, then that alpha cannot be in the normalizer.
Exactly. The normalizer is the set of tame elements. Even if they aren't field automorphisms themselves, they still respect the boundary of the field automorphisms under conjugation. Since our alpha to the n actively shifts the Q sub 2 base structure, it is far too wild to be in the normalizer.
And this immediately gives us Theorem 3.2, the big structural chaos result.
Theorem 3.2, the set of out of G sub k conjugates of out of K is infinite.
Okay, that covers the linkage lemma and the statement of Theorem 3.2. Have we missed any nuances on the definition of normalization?
I think we've thoroughly unpacked it. The normalizer is the set of tame elements.
Yep.
We know our alpha is wild. Let's prove the contradiction.
The proof is very swift. It just relies on the previous sections. It says it suffices to show that the normalizer has infinite index in out of G sub k.
Right. And we prove that the infinite sequence of non-trivial powers, alpha, alpha squared, alpha cubed, and so on, are all outside the normalizer. Since we have infinitely many elements outside the normalizer must have infinite index in out of G sub k.
And infinite index means infinitely many distinct causates, which translates directly to infinitely many distinct conjugate subgroups that are isomorphic to out of k.
And that formally closes the loop on the structural investigation for p equals 2. The abstract symmetries create infinite instability for the finite symmetries of the field.
So that covers the central logical deduction, linking the infinitude of the non-preserving powers of alpha to the infinite index of the normalizer. Have we missed any nuances on why infinite index guarantees infinite conjugates?
I think we've thoroughly unpacked it. Each distinct causate of the normalizer corresponds to a distinct conjugate subgroup, so infinite index means infinite conjugates. Let's look at the formal consequences.
Corollary 3.3 just formalizes the conclusion: non-normality and infinite conjugate subgroups. This reaffirms that these two adic fields are profoundly non-anabelian.
Right. But then Corollary 3.4 offers this fascinating contrast. It looks at the center of the outer automorphism group, Z of out of G sub k. These are the elements that commute with everything. And the corollary states that any element in the center must act as the identity automorphism on the additive module k+.
So, despite the overall infinite wildness of out of G sub k, the centralized elements are forced to be incredibly tame on the field structure. Why does the chaos of alpha enforce this tameness on the center?
It's a great question. The proof relies on the fact that if a central element, let's call it gamma, commutes with our alpha, the geometry of that commutation relation, combined with the fact that gamma has to be Q2 plus preserving because central elements normalize everything, forces gamma plus to be the identity map on K plus. Our extreme, non-trivial shear alpha acts as a kind of algebraic purity filter. It ensures that any element that commutes with it cannot introduce any discernible linear displacement on the field structure.
That's a powerful implication. The wild part of the group, represented by alpha, actually constrains the center to be harmless with respect to the field's additive structure. So that concludes section 3. We have the infinite instability of out of k, contrasted by the unexpected tameness of the center. Have we missed any nuances regarding the constraints placed on the center?
I think we've thoroughly unpacked it. The shear element alpha acts as an algebraic litmus test, forcing all central elements to be trivial on K+. Let's proceed to section 4 and the Hodge state instability.
Section 4, instability of crystalline representations. This section translates the additive wildness of alpha plus into the multiplicative wildness of alpha cross, which is what we need for working with representations.
Yes, and to do this, we use local class field theory, specifically the reciprocity map rec sub k. This provides an isomorphism between the multiplicative group of k and the abelian part of G sub k. This lets us translate the action of alpha from group theory to the multiplicative field structure, defining alpha cross as the induced automorphism on the unit group O sub cos.
So we're looking for the unit instability analog of theorem A.
And the ultimate goal remains to show that a crystalline representation rho is not unintrinsically Hodge-Tate, meaning that rho circle alpha is no longer Hodge-Tate.
Okay, that covers the setup for p-adic representations, including the reciprocity map and the definition of alpha cross. Have we missed any nuances?
I think we've thoroughly unpacked it. We now need the multiplicative analog of the non-preserving result. Let's look at lemma 4.2.
Lemma 4.2 proves the multiplicative wildness of alpha. Assertion V states that the intersection of the base units, O sub Q2 cross, with the twisted base units, alpha and cross of O sub Q2 cross, is not open.
And this is the critical technical step. We're dealing with topological groups here. If the intersection were open, it would imply that the twisted base units are topologically close to the original ones, a sign of tameness. The fact that the intersection is not open implies a profound topological shift. Alpha cross actively drags the base field units out of their original topological space.
And this unit instability is proven by translating the unipotency property, t minus I squared equals 0, into the multiplicative domain via the p-adic logarithm map.
Yeah.
And that leads to the same contradiction as in section 2 if you assume the base units are preserved.
Right. The non-preservation of the Q sub 2 structure is now confirmed in both the additive K plus and the multiplicative O sub cos realms. The abstract shear alpha just warps the field's fundamental coordinate system.
So that covers the detailed multiplicative instability result, showing that the action alpha cross shifts the base units such that their intersection is topologically trivial. Have we missed any nuances on the role of the logarithm in translating addition to multiplication here?
I think we've thoroughly unpacked it, recognizing that the log map is implicitly the key to connecting the unipotent additive structure to the unit structure. Let's generalize.
So now we construct the representation row that is destined for destruction. Theorem 4.4 asserts the existence of an irreducible abelian crystalline representation row that is not intrinsically Hodge state.
Right. The proof details the construction of rho as a composite map. G sub k is first abelianized, then it's mapped to the unit group O sub k cross via the reciprocity map, and finally embedded into the linear automorphisms of the vector space K+.
And this specific representation row is known to be crystalline, a geometrically rigid, very desirable property.
But the instability of alpha immediately corrupts it. Nishio cites a lemma from Hoshi, which proves that the unit group non-preservation that we just discussed translates directly into the failure of the Hodge-Tate property for the twisted representation, rho circle alpha.
That conclusion is so compelling.
Yeah.
Out of G sub k is so chaotic that it contains these simple group-theoretic symmetries, like the unipotent shear alpha, that are capable of destroying even the most rigid geometrically stable representations defined over the field.
The chaos we saw structurally translates directly into a chaotic geometry for p-adic Galois representations. This confirms the vast power of out of G sub k and completes the paper's mission for the p=2 case.
Okay, so that covers the construction of the crystalline representation row and the final proof that it is unstable. Have we missed any nuances on the overall link between alpha's group action and the resulting field instability?
I think we've thoroughly unpacked it. The non-preservation of the Q sub 2 structure, whether it's additive or multiplicative, is the root cause of both the infinite group chaos and the geometric instability of representations. Let's confirm the specific dimension result.
Corollary 4.5 specifies the result for the minimal non-trivial case, where the dimension d sub k is 2. The existence of this representation and the wild automorphism is confirmed even for the simplest field that satisfies the necessary condition of containing the fourth root of unity.
And the paper then concludes with acknowledgments to Yuichiro Hoshi for discussions, and to the author's partner, Yu Nishio. The references provide the necessary foundation in mono-anabelian geometry and p-adic Hodge theory.
And the final metadata, including the author's email address, concludes our linear deconstruction of the document. So that concludes the entire document, from the initial title to the final email address, adhering strictly to the linear progression protocol. Have we missed any final nuances of the source document structure?
I think we've thoroughly unpacked every definition, theorem, and technical step required. We are ready for the final thought.
This deep dive into Nishio's 2025 paper reveals a profound truth. The p-adic Galois group G sub k harbors abstract symmetries in out of G sub k that are far beyond the symmetries of the field itself, out of k. The gap between the group and the field is infinite.
Yeah, the constructed unipotent automorphism alpha is the ghost in the machine. It's this simple, non-diagonalizable shear that ensures the field automorphisms are not a normal subgroup, creating infinite structural variance. And it's also what instantly breaks these geometrically nice properties, like the Hodge-Tate property.
It's a powerful reminder that in advanced algebra, the group structure contains information that the field structure sometimes fails to regulate, especially in this tricky p=2 dyadic case. The p-adic structure is inherently unstable against its own internal abstract symmetries.
And, we've seen that crystallinity, this hallmark of stability derived from geometry, can be instantly destabilized by a purely group-theoretic operation. This raises an important question for you, the listener, to consider. We've now characterized the instability caused by this element alpha. Given that representations are so easily broken by these structural symmetries, should mathematicians now focus less on finding stable representations and more on developing a framework to systematically characterize the entire unstable space created by the action of out of G sub k? Welcome to the Deep Dive, where we take your dense sources and carve out the core knowledge. Today's mission is, well, it's arguably the most ambitious we have ever undertaken. We are diving deep into the algebraic heart of local fields, tackling an extremely specialized document in advanced number theory.
Our source today is the paper on the Outer Automorphism Groups of the Absolute Galois Groups of p-adic local fields by Yu Nishio. And this work, dated December 2025, isn't just standard theory. It's really a fundamental exploration into the limits of algebraic reconstruction. And it specifically focuses on the most challenging case in all of p-adic theory, when p equals 2, the two adic fields.
Right, and the listener request here, it demands nothing less than extreme thoroughness. Our mandate is granular deconstruction. Our focus is the structure of these two adic fields, we'll call the field K and its base Q2. And we're going to be looking at how their intrinsic, their finite symmetries relate to a much larger, much wilder group of abstract symmetries. We are proceeding linearly through the text, stopping at every single paragraph for verification.
Yeah, and this is a journey right into the heart of what's called anabelian geometry. This was Grothendieck's profound vision, trying to understand a complex object like a number field, purely by studying the structure of its fundamental group. So we really need to define our cast of characters precisely. We have the two-adic local field, K, its absolute Galois group, K, which holds all the algebraic extension data, and then the outer automorphism group out of Galois, which governs the abstract symmetries of that group structure itself.
That sets our mission and defines the basic algebraic landscape. So let's just dive right in. Let's move immediately into the title and abstract to establish the core problem Nishio is aiming to solve.
All right, so the title is On the Outer Automorphism Groups of the Absolute Galois Groups of Two-Adic Local Fields.
That title is a whole thesis statement in itself. Okay, let's confirm the core definitions we need to operate with. What exactly defines a local field crick in this context, and why is it called mixed characteristic?
All right, so a local field here is a very specific, highly structured field. It's essentially a finite extension, K, of the two adic numbers, Q2. And that mixed characteristic label is absolutely crucial. The field K itself has characteristic 0, but when you look at its residue field, what you get after you sort of reduce it modulo the maximal ideal, that has characteristic P2. And this fundamental mismatch in characteristics, that's the source of so much of the complexity here. So it drives all these results.
Okay, and we've introduced the Absolute Galois Group, QK. What about the Outer Automorphism Group out of Greek? Why are we studying the outer automorphisms? What does that get us?
So Greek is the Galois group that encodes all the symmetries of the algebraic closure. Think of it as the total symmetry group.
Yeah.
Now, out of Greek is the group of all automorphisms of Greek, but we divide out or mod out the inner automorphisms.
Which are just simple conjugations, right?
Exactly. They're basically trivial structural changes.
Yeah.
We only care about out of Greek because inner automorphisms are, not that interesting. Out of Greek represents the deep, hidden structural symmetries of the Galois group itself. If out of Greek is large and complex, it means the group structure is way richer than the field structure might lead you to believe.
Understood. Now, the first sentence of the abstract connects us directly to the framework. It says, abstract. In the present paper, we studied the outer automorphism groups of the absolute Galois groups of two adic local fields from the point of view of anabelian geometry. Let's elaborate a bit more on what anabelian geometry really is.
It's a massive program started by Grothendieck, and it's a really radical idea. It's about reversing the usual process. So instead of starting with an algebraic object like our field K and then calculating its fundamental group dk, you start with just the group key and you try to reconstruct the entire field K from it.
Then does that work?
It works beautifully for some things like curves, but for p-adic fields it sort of breaks down. When p is odd, the field K is known to be not anabelian in the strictest sense, and that's because its group K has symmetries, these elements in out of GK that just do not correspond to any symmetries of the field itself, the ones in out of K.
Ah, so the two adic fields, the P2 case, are the ultimate testing ground to see just how badly this reconstruction fails. If the difference between the field symmetries and a K and the group symmetries out of GK is huge, then the field is considered highly non-anabelian.
Exactly that. And the historical context which the paper builds on shows that for odd primes, this difference is already large. Out of K is much, much bigger than out of K. Nishio's work is about tackling P2, where the complexity from the two-adic arithmetic is just far greater to see if the same kind of chaos holds true.
Okay, let's do our first completeness check. That covers the title, the author, and the fundamental framework of anabelian geometry for this abstract's first sentence. Have we missed any nuances regarding the initial setup?
I think we've thoroughly unpacked it. We're focusing on Q2 and the basic role of out of Greek. I think we're good to proceed to the background results.
Great. So let's see what the abstract says next.
The document first reminds us of the starting relationship. It says, let us recall that it is well known that the natural homomorphism from the automorphism group of a mixed characteristic local field to the outer automorphism group of the absolute Galois group of the given mixed characteristic local field is injective.
Okay, so this injective embedding, which we can write as out of games embeds into out of grunk, that's our starting line. It lets us view the finite group of field symmetries out of grunk as this sort of contained, tame subgroup inside the possibly infinite wild group of abstract symmetries out of grunk.
That perspective is absolutely essential.
Yeah.
If out of K were equal to out of K, the field would be perfectly anabelian. But prior work for odd primes, for odd P, already showed this wasn't the case, and the abstract cites this finding. Moreover, Hoshi and the author of the present paper proved that for absolutely abelian mixed characteristic local fields with odd residue characteristic P, this subgroup is not normal and has infinitely many distinct conjugates.
Let's quickly define that setting. Absolutely abelian mixed characteristic local fields. What does that mean?
It just means the field extension over key P is a Galois extension, and its Galois group is commutative. It simplifies the setup just enough to make it manageable.
And the consequence for odd P was non-normality and infinite conjugates.
Right. And when a subgroup H isn't normal in a larger group G, it means you can conjugate it by elements of G and transform H into a totally distinct, though isomorphic, copy of itself.
Yeah.
The infinite distinct conjugates result meant that for odd primes out of K contained this infinite reservoir of wild symmetry that just fundamentally destabilized the set of field symmetries out of K.
And this leads us directly to main result 1 of Nishio's paper extending this chaos to the PU2 case.
Yes. As a result in this direction, one of the main results of the present paper is the assertion that if a p-adic local field satisfies certain conditions, then the set of conjugates is infinite, which thus implies that this subgroup is not normal.
This is the critical extension because PU2 introduces all these unique complexities, right?
It really does, especially concerning the units modulo 4 and the presence of the fourth root of unity. A lot of the techniques developed for odd primes just fail spectacularly. Nishio succeeds by finding the specific, certain conditions required to make the construction work and proves the same structural chaos exists in this dyadic world.
Okay, completeness check number 2. That covers the discussion on the non-normality and infinite conjugates result, spanning prior work and the paper's first main assertion. Have we missed any nuances regarding the complexity jump from odd P to P2?
I think we've thoroughly unpacked it. We've emphasized that P2 introduces these unique algebraic complexities that have to be overcome here. Let's proceed to the second main result, which is about representations.
Right, the geometric side of things.
The abstract moves to p-adic representations, and it cites Hoshi's work for odd P, showing an automorphism can destroy what's called the Hodge-Tate property of a representation.
Okay, for the listener, let's ground this concept. A p-adic representation is basically how we translate the abstract group action of Grec into concrete linear algebra. So you're mapping Galois elements to matrices that act on a vector space V. And a Hodge-Tate representation is considered nice or geometrically sound. It's sort of a hallmark of stability in p-adic Hodge theory.
Yeah, and the prior results showed that autocorrect contained an element that, when you used it to twist a nice representation rho into a new one, rho composed with alpha, the result was a representation that was no longer nice. It wasn't Hodge-Tate anymore. It demonstrated that these abstract group symmetries were geometrically disruptive.
So main result 2 is the p-key2 analog.
Exactly. As a result, in a direction that is different from the above direction, another main result is the existence of a pair of a representation and an automorphism that is similar to the above pair in the case where P keys 2.
This confirms the same geometrical destructiveness for P2.
It does. The paper finds a representation that is initially crystalline, which is a really powerful form of Hodge-Tate, but it can be destabilized by the action of one of these wild automorphisms from out of gig.
The final keywords in the abstract introduce monoanabelian geometry and alt-intrinsically Hodge-Tate.
Monoanabelian geometry is the tool used throughout the paper. It's this functional reconstruction of key invariants directly from the group GIC. And alt-intrinsically Hodge-Tate defines total stability. It means a representation that remains Hodge-Tate even after being twisted by any automorphism of GEC. The proof of Theorem D shows that the representations they construct are emphatically not alt-intrinsically Hodge-Tate.
All right, that's our third check. That concludes the abstract, covering the key results about Hodge-Tate disruption for P2. Have we missed any nuances regarding the definition of alt-intrinsically Hodge-Tate?
I think we've thoroughly unpacked it, noting that the paper's goal is to demonstrate instability. Let's move to the introduction on page 2.
Right, where the central question gets quantified.
The introduction starts by formally establishing all the variables. P is a prime, K is an extension of QP, G key is the Galois group, and the central relationship is that injective embedding, out of K inside out of G.
And we really need to elaborate on the consequence of out of K being finite, while out of K is potentially infinite.
Right. In the abstract anabelian sense, GIC is supposed to perfectly define K. If the symmetries align, if out of K equals out of Greek, then the group structure perfectly mirrors the field structure. But when out of Greek is vast, it means Greek contains all these group-theoretic symmetries that have absolutely no arithmetic meaning. You can't trace them back to field operations like multiplication or addition. And this excess, this wildness, is precisely the difference the paper is setting out to investigate.
The paper explicitly states that for odd P, the equality never holds. This led to the historical conclusion that these fields are not anabelian, so the goal here is purely to investigate the magnitude of this gap.
Exactly. For odd primes, we knew the gap existed, we knew it was infinite. The major hurdle was repeating this feat for the P2 fields, which are algebraically much, much more stubborn.
Okay, completeness check number 4. That establishes the context, defining the difference between out of K and out of Greek as the central interest. Have we missed any nuances regarding that historical non-anabelian conclusion?
I think we've thoroughly unpacked it, emphasizing that prior work focused on p-odd. Let's proceed to the new challenge.
The dyadic case.
The paper states it plainly. On the other hand, no similar results were known in the case where p equals 2. Thus, it is a natural question to ask how far Auki differs from Auki in the case where p equals 2.
And this confirms the technical void Nishio is filling. The difficulty of P2 is often linked to the behavior of two adic units, right? The multiplicative elements that are close to 1.
Yes, for P2, the standard tools of p-adic theory, like the logarithm map, they all require very careful adjustments because of torsion elements like plus or minus I.
So to overcome this, the paper uses a powerful tool from mono-anabelian geometry, the reconstruction algorithm.
Exactly. The author introduces the additive modules, K+, which is the field K treated just as a vector space over Q2.
And the absolute key is that this abstract group, out of Go, can act on this very concrete vector space, K+.
Yes. That reconstruction algorithm is the whole game. It provides a functorial way to recover the additive structure K+, directly from the group G. So any automorphism, alpha, in out of Greek, must induce a linear transformation, alpha plus, on K+. And here's the crucial part. If alpha actually came from a field automorphism in out of K, its induced action, alpha plus, would have to fix the base field Q2. This linear action is the litmus test for wildness.
So we're hunting for an element alpha in out of Greek whose induced linear action alpha plus violates the most basic rule of field automorphisms. It doesn't fix Q2.
That is the entire strategic goal. And that leads us directly to Theorem A.
All right, check number 5. That covers the motivation for studying P2 and the key technical tool, the action of out of Greek on the additive structure K+. Have we missed any nuances regarding the significance of the action coinciding with the out of K action only on the restriction?
We've thoroughly unpacked it. The restriction coinciding just means field automorphisms are tame on K+. We're on the hunt for out of Greek elements that are wild. Let's look at Theorem A.
Let's do it.
So Theorem A, which is later called Theorem 2.5, establishes the existence of this wild element alpha. It starts with two necessary conditions. 1. The field of K contains a primitive fourth root of unity. 2. The finite extension K over Q2 is Galois, and moreover, the Galois group is abelian.
Condition 1, containing the fourth root of unity, let's just call it I. That's the algebraic handle needed to make the P2 arithmetic sufficiently complex for the construction to work.
And condition 2, the absolutely abelian requirement, simplifies the field extension just enough to ensure the generators of the Galois group are manageable. It lets Nishio write down the precise group relations that are necessary.
Okay, now for the conclusion of the theorem.
Then there exists an outer automorphism alpha of D such that for each non-zero integer n, if one writes alpha to the n plus for the action of alpha to the n on K plus, then alpha to the n plus of Q2 plus is not equal to Q2 plus.
So this is the existence proof. This is the non-field-like automorphism, alpha. Its induced action, alpha plus, fails the most fundamental test. It doesn't even map the base field Q2 back to itself as a set. If you take an element Q in Q2, alpha plus of Q length somewhere outside of Q2. Why is that single violation so definitive?
Because a true field automorphism, sigma, must fix the base field Q2 element-wise. Sigma of Q has to equal Q. If alpha moves Q2 around, it just cannot be a field automorphism.
Yeah.
This is the central technical achievement, constructing an automorphism alpha that lives purely in this abstract realm of Drake, and whose action is totally inconsistent with the basic axioms of field symmetry.
And the emphasis on for each non-zero integer n immediately tells us that we have an infinite supply of these wild automorphisms, alpha, alpha squared, alpha cubed, and so on.
Exactly. And this infinite supply is what's going to lead to the structural chaos in the next set of theorems.
Okay, completeness check 6. That covers theorem A, establishing the existence of a non-trivial automorphism alpha that fails to preserve the underlying Q2 additive module. Have we missed any nuances on why preserving the Q2 structure is necessary for a field automorphism?
I think we've thoroughly unpacked it. Fixing Q2 is axiomatic for field automorphisms. Alpha violates this. Let's look at the subsequent theorems that are built on this existence.
On to the consequences.
Theorem B, which is later Theorem 3.2, converts the existence of alpha into that structural chaos we anticipated. Suppose that the two conditions are satisfied. Then the set of out-of-G conjugates of the subgroup out of K is infinite.
So the existence of this single wild element alpha immediately implies a non-normality and infinite conjugates of out of K for the P2 case.
It does. It relies on a strategic linking lemma we'll get to in section 3. But the logic is, since alpha acts wildly, it moves Q2, it can't belong to the normalizer of out of K. And because we have infinitely many distinct powers of alpha, the normalizer must have infinite index in out of Gio, which directly means you get infinite conjugate subgroups.
And theorem C just formalizes this instability.
Right. The subgroup out of K is not normal.
Yeah.
There exist infinitely many distinct subgroups of out of K isomorphic to out of K. It just confirms that the field symmetries are highly unstable within this vast group of abstract symmetries.
Then the final major consequence, theorem D, takes us back to the geometric side.
Yes. There exists a finite extension K of Q2, a Q2 vector space V of dimension 2, and a continuous representation ρ that is irreducible, abelian, crystalline, but not out intrinsically Hodge-Tate.
This is the geometric punchline.
It is. Nishio demonstrates a representation, ρ, that is initially pristine. It's irreducible, a building block, abelian, so it has a simple structure, and crystalline, so it's geometrically rigid and Hodge-Tate. And yet, when you twist it by that wild automorphism alpha from theorem A, it loses the desirable Hodge-Tate property.
So the abstract group chaos has a direct destructive impact on some of the most valued invariants in p-adic geometry.
Precisely. It proves that the niceness of a representation isn't intrinsic to the field structure, but it's highly susceptible to these non-field-like symmetries lurking within out of Grank.
Okay, check number 7. That concludes the main results, showing that the non-field-like automorphism alpha leads to both infinite instability of out of K and instability of the crystalline representation Reno. Have we missed any nuances regarding how these two results relate?
I think we've thoroughly unpacked it. Both are consequences of out of Grank containing these strange group theoretic symmetries that just cannot be explained by field structure alone. Let's proceed to the notational conventions.
Right. We need to get into the weeds of the proof, and that starts with the notation.
Okay, section 0 provides the necessary algebraic dictionary. We should probably just highlight the few critical structures that are central to the whole mono-anabelian approach. For instance, the paper defines G-ab, the abelianization of the Galois group, and G-ab/A-tor, the free quotient where you remove torsion. But crucially, the theory relies on isolating the p primary parts. The notation H super p for the maximal pro-p quotient of a profinite group H is essential for focusing strictly on the two-adic behavior that drives the wild inertia.
And the most important definitions are the field invariants that have to be reconstructed from the group G.
Yeah, we have dk, the dimension of the extension, which tells us the dimension of the resulting Q2 vector space K+. But the most complex arithmetic happens in the unit group, scripto cross, and the paper uses this notation, scripto less thank, for the 1 units, which are the elements of the multiplicative group that are closest to 1.
Why are these 1 unit scriptoless thank so strategically important here?
Because their structure is mathematically equivalent to the wild inertia subgroup, P of GK, of the Galois group. And P of GK is the most non-abelian, the most chaotic part of the Galois group. By recovering these 1 units from the wild inertia via the reconstruction algorithm, we get the additive vector space K+ through an implicit logarithm map. This is why the notation for K+ is defined using a tensor product with the rationals. It's the completion of the abelianized wild inertia group.
So if we can build a specific automorphism alpha that acts wildly on the wild inertia P of G, that action translates through this whole reconstruction process into a simple but non-field-like linear transformation on the vector space K+.
That is the entire strategy, and we're now ready to see it executed in section 1 where the unipotent automorphism alpha star is constructed.
All right, completeness checks 8 and 9 are implicitly covered. We've defined the key notations and their strategic importance. Let's jump into section 1.
So section 1 aims to prove the existence of an automorphism, alpha star, that satisfies a certain unipotency condition. It starts by just reiterating the reconstruction process. You start with the abstract group G, and the mono-anabelian algorithms allow you to recover all the field invariants, including that additive module K+ of G.
And we have to remember the crucial assumptions we inherited from Theorem A, which guide this whole construction.
Right. We assume the characteristic P of G is 2, and that A of G is greater than or equal to 2. That second condition ensures the field contains the fourth root of unity, I, which provides the necessary 2 torsion complexity.
Okay, the key ingredients are set. We have P2, we have I, and we have this functional isomorphism linking the wild inertia P of G to the vector space K+ of G. Let's look at the topological structure used to define G.
We turn to proposition 1.1, which is based on Deikert's work, and it provides the precise topological generators for G. These are sigma for Frobenius, tau for tame inertia, and x0 by 1, up to x of G for the wild inertia generators. The wild inertia subgroup P of G is generated entirely by these PS.
The proposition gives 3 defining relations. Relation 2 is pretty standard for Frobenius action, but relation 3 is this extremely complex nonlinear relation that links the generators of the wild inertia. It's a bit of a monster.
It is a monster, yeah. It's long, and it includes commutator terms like the bracket of by 1 and by 2, which are what make G non-abelian. But strategically, this relation is the key input for linearizing the group. When we move from the non-abelian group P of G to the abelian vector space K+ of G, this relation causes certain dependencies among the generators.
And that dependency is what dictates the basis of K+ of G.
Precisely. Let Y be the additive image of the generator, 11. Lemma 1.2 states that K+ of G is a Q2 vector space of dimension D of G. However, Lemma 1.3 states the D of G elements Y1A yard of G form a basis of the Q2 vector space K+ of G.
Why is Y missing? This has to be the core structural payoff of those complex relations.
It is. Because of the dependence established by Deikert's relation 3, the generator x0 is algebraically dependent on the other generators in the abelianized torsion quotient. Therefore, its image, y0, is linearly dependent on the remaining basis vectors, y1 through yard of G. The existence of a basis without y0 is the confirmation that those complicated group relations has simplified the additive structure into a clean D of G dimensional vector space.
And lemma 1.4 confirms a crucial detail. Yard of G-1 is a non-zero element. Since it's a basis vector, this has to be true, but it's stated explicitly because this is the specific vector that will be used to define the non-trivial shear.
That's correct. The basis gives us our coordinate system. Now, we use this coordinate system to construct the unique automorphism alpha star.
So that's completeness checks 10, 11, and 12. We've set up the reconstruction, used Deikert's relations, and established the basis for our vector space. We are ready to define the shear.
Definition 1.5 defines alpha star as an automorphism of the group G. It's the identity on sigma, tau, and all the causes except for 1. Alpha star of xd of G is equal to xd of G times xd G minus 1.
This is a very targeted multiplicative operation at the group level. And when you translate it into the additive vector space K+,
it becomes a simple linear shear. Yard of G maps to yard of G plus yard of G minus 1. All the other basis vectors are fixed.
This transformation is designed to be as minimal as possible while still being non-trivial. And this leads to the critical algebraic result, Theorem 1.6. The unipotency condition.
Right. Theorem 1.6 proves that for the induced action, let's call it T, we have the equality. It's written as alpha plus 2 equals 0. The quantity alpha star to the power n plus minus the identity squared is equal to 0.
What does that condition, T minus I squared equals 0, tell us about the geometry of the map T?
It means T is a unipotent operator. It's a transformation matrix that is very, very close to the identity matrix. In linear algebra terms, T has ones on the diagonal and then maybe a few non-zero entries just above or below. Specifically, it's a shear. The transformation T only shifts one coordinate by a multiple of another, and applying that shear operation twice does nothing new.
The proof immediately confirms its non-triviality. If T were the identity, it would mean yard of G minus 1 was 0, which contradicts lemma 1.4.
Exactly. We have successfully constructed an automorphism alpha star of G that is not the identity, yet it acts minimally. It obeys this unipitancy constraint, and we have an infinite number of distinct powers of this automorphism.
Okay, check 13. That covers the full construction and algebraic proof of the unipotent automorphism alpha star acting on K plus of G. Have we missed any nuances regarding how the power n distinguishes alpha to the n?
I think we've thoroughly unpacked it. The integer n means we have infinitely many distinct automorphisms. Let's look at the corollaries.
The structural consequence is immediate in corollary 1.7. The outer automorphism group out of G is infinite.
This is the first major payoff for the PE2 case. Since the alpha to the n plus actions are all distinct, non-trivial linear transformations of the field's additive structure, they must represent distinct infinite automorphisms in out of G. This confirms the structural chaos.
And the text notes the crucial boundary condition in remark 1.8. If the dimension d of G is 1, so the field is just Q2, the result is trivial. The complexity requires d of G to be at least 2.
The structural necessity for having multiple wild inertia generators, those X, is what creates the vector space and enables the shear action to be constructed. Without enough dimension, you can't write down the ghost in the machine.
Okay, check 14 is done. That concludes section 1. We now have our infinitely many unipotent, non-trivial, wild automorphisms. We just need to prove that these elements are indeed non-field-like.
Which brings us to section 2.
Applying alpha star to the field structure.
So section 2 starts by formalizing the definitions of characteristic and preserving. These definitions are the litmus test for field-like behavior.
A linear map is Q2 plus characteristic if it maps the base field Q2 back to itself as a set. It's Q2 plus preserving if it maps every element of Q2 to itself.
Every field automorphism must be Q2 plus preserving. So if we can show our constructed alpha star fails the weaker characteristic test, we confirm its wildness beyond any doubt.
Before the final proof, lemma 2.2 introduces these crucial constraints imposed by the trace and norm maps. Why does an abstract Galois automorphism alpha have to respect the field's trace map?
The trace map, which sums the conjugates of an element, is a fundamental invariant that comes from the field extension itself. The lemma ensures that any automorphism of the Galois group has to act compatibly with it. Most importantly, it requires that the kernel of the trace map, the elements that average to 0 under the group action, must be preserved by alpha plus. This provides the necessary algebraic rigidity to force a contradiction.
We use the constraints from the trace kernel and the unipotency property to force the contradiction. Okay, checks 15 and 16 are covered. We have the definitions and the constraints. Let's see the proof.
Lemma 2.3 is the core contradiction proof. It's demonstrated here for the simplest case. The quadratic extension k equals q2 of I, where I is the fourth root of unity.
And we assume for contradiction that the induced action t, which is our alpha to the n plus, is q2 plus characteristic. This means t of 1 must be some element b in q2. And because of the trace kernel constraints on the basis element I, t of I must be c times I, where c is also in q2.
Right. And since t is linear, we can apply the transformation to a general element x plus yi, where x and y are in q2. And the key step is applying the unipotency property. The quantity t minus I squared applied to x plus yi must equal 0.
The resulting equation simplifies to x times the quantity b minus 1 squared plus y times the quantity c minus 1 squared times I equals 0. And since x and y are arbitrary and 1 and I are linearly independent over q2, this identity has to hold term by term.
Which forces b to equal 1 and c to equal 1. But if b is 1 and c is 1, the map t fixes both basis elements. So t must be the identity automorphism.
But wait a minute, we proved in theorem 1.6 that t is not the identity automorphism.
That's the perfect contradiction. The only unipotent shear that is Q2 plus characteristic is the trivial map. Since we know our map is non-trivial, our initial assumption must be false. Conclusion. Alpha to the n plus is not Q2 plus characteristic. It moves the base field Q2.
That is just a stunning piece of algebraic logic. The wildness is confirmed because the constructed automorphism, while algebraically simple, it's just a shear, is too restrictive to also be a field symmetry. All right, check 17. That covers the crucial contradiction proof. We've linked unipotency to the trace constraints to prove alpha star moves the base field. Have we missed any nuances on why the unipotency relation is so constraining?
I think we've unpacked it. The unipotency restricts the transformation to a simple, non-diagonalizable shear. If a shear fixes the basis, it must be trivial, but alpha star is designed to be non-trivial. Let's look at the generalization. The paper then uses lemma 2.4 to generalize the result to any absolutely abelian field K that meets the conditions. It relies on DREC being a characteristic subgroup of a simpler group, which means the non-characteristic property of the wild automorphism is preserved upon restriction.
And Theorem 2.5, the final statement of our Theorem A, is thus formally proven.
Right. There exists an automorphism alpha, such that alpha to the n is not Q2 plus characteristic.
Check 18 done. We have our infinite supply of confirmed wild automorphisms for the PQ2 case. The next logical step is using this to prove the infinite instability of out of K,
which is section 3.
Non-normality and infinite conjugacy.
Section 3 is dedicated to proving theorems B and C, and lemma 3.1 is the vital bridge, linking the technical result of theorem 2.5 to the group theory of normalization. The lemma states, if the image of alpha is contained in the normalizer of out of K, then alpha is Q2 plus preserving.
So this is the operational litmus test. If an abstract symmetry alpha is tame enough to normalize the field symmetries, then alpha must be arithmetically tame. It must fix the base field.
And since we just proved that alpha to then n fails the test of being characteristic, which is weaker than preserving, it automatically follows that alpha to then cannot be in the normalizer.
This directly proves Theorem 3.2, our Theorem B. The set of conjugates is infinite. Check 19 is a go. We have the linkage lemma and the setup for the proof. Let's see the deduction.
The proof is just a neat logical cascade. To show infinite conjugates, we have to show that the normalizer of out of K has infinite index in out of gank.
And since we have an infinite number of distinct, non-preserving elements, none of which are in the normalizer simply can't regulate their action.
Which forces the normalizer to have infinite index. Each coset of the normalizer corresponds to a distinct conjugate subgroup. Therefore, out of gank is infinitely large and infinitely destabilizing to the field symmetry group out of K. This solves the central structural problem for P2.
Check 20. That covers the central logical deduction. Have we missed any nuances on why infinite index guarantees infinite conjugates?
I think we've unpacked it. Each distinct coset corresponds to a distinct conjugate, hence infinite conjugates. Let's look at the final consequences in this section.
Corollary 2.3.
It just formalizes the conclusion. AdLP is not normal, and there are infinitely many distinct subgroups of out-of-Grach isomorphic to it.
But then Corollary 3.4 reveals a contrasting tameness at the heart of the group.
Yeah, this is interesting. It says that any automorphism that comes from an element in the center of out-of-Grach must act as the identity on the additive field structure K+.
Why, if out-of-Grach is so chaotic, does its center, the elements that commute with everything, act trivially on the field structure?
It's a beautiful constraint imposed by the existence of our wild element alpha. Any element in the center has to commute with alpha. Also, it has to normalize out of K. The combination of being Q2 preserving and commuting with our non-trivial unipotent shear is so restrictive that it forces the element to be the identity on the entire space K+. The wildness of alpha limits the freedom of the central elements.
Okay, check 21. That concludes section 3, showing the infinite instability contrasted by the tameness of the center. Have we missed any nuances regarding the constraints placed on the center?
I think we've thoroughly unpacked it. The shear element alpha acts as a litmus test, forcing all central elements to be trivial. Let's proceed to section 4 and the Hodge-Tate instability.
The geometric side of the story.
Section 4 connects our abstract group chaos back to p-adic Hodge theory. We rely heavily on the reciprocity map, REC, which provides a crucial link between the field's multiplicative units and the abelian part of the Galois group.
And the ultimate goal here is to prove Theorem D, the existence of a representation row that is Hodge-Tate, but not intrinsically Hodge-Tate.
To do that, we need the multiplicative analog of our non-preserving result, so we define alpha subcross as the action of the group automorphism alpha on the unit group.
Check 22, the setup for section 4 is complete. We're ready for the multiplicative instability result.
Lemma 4.2 establishes that alpha is also multiplicatively wild. It proves assertion V. There exists an automorphism alpha such that the intersection of the twisted base units and the original base units is not open in the original base units.
What does not open mean in this context?
It's a topological statement. It means the action of alpha subcross twists the base unit group so fundamentally that it destabilizes its relationship to itself. It's the multiplicative equivalent of Theorem 2.5. If alpha were a field automorphism, this twisting could not happen.
And this wild action on the unit group is key, because the units are the arithmetic input into the representation construction via that reciprocity map.
Exactly. The proof relies on the same contradiction we used in section 2. only it's translated from the additive space K plus to the multiplicative space of units via the logarithm map. If alpha subcross were stable on the base units, the unipitancy constraint would force it to be trivial, which we know it is not.
Check 23. That covers the detailed multiplicative instability result. Have we missed any nuances on the role of the logarithm in translating addition to multiplication here?
I think we've recognized that the log map is implicitly the key to connecting the unipitant additive structure to the unit structure. Let's generalize.
Okay. Proposition 4.3 generalizes this to all relevant fields. And this sets the stage for the final result, theorem 4.4.
Right, which guarantees the existence of the unstable crystalline representation, HEAL. If we look at the construction of a row, it's a composite map. It takes elements from the Galois group, pushes them to the abelian part, maps them to the units via a character chi, and then embeds this unit action into a linear transformation.
And the proof confirms that this constructed representation row is initially irreducible, abelian, and crystalline. It's geometrically stable.
The instability comes when we twist it. The proof cites a result by Hoshi, which directly links the multiplicative instability of the base units under alpha subcross to the destruction of the Hodge-Tate property.
The logic is complete. The abstract automorphism alpha, constructed from those complicated group relations for p-2, fails to preserve the simplest arithmetic structures of the field. And this failure, in turn, forces the destruction of the geometric properties of the crystalline representation row.
The ghost in the machine now has a documented destructive power in both structure and geometry.
Check 24. That covers the construction of the crystalline representation and the final proof that it is unstable. Have we missed any nuances on the overall link between alpha's group action and the resulting field instability?
I think we've thoroughly unpacked it. The non-preservation of the Q2 structure, whether additive or multiplicative, is the root cause of both the infinite group chaos and the geometric instability. Let's look at the final corollary.
Corollary 4.5 gives us a specific example for the simplest case, dk equals 2. There exists a two-dimensional crystalline representation over Q2 that is unstable.
This just provides a concrete example of the general theory from theorem 4.4. The document then concludes with the acknowledgments, thanking collaborators like Yuichiro Hoshi, and the extensive reference list.
Okay, final check, number 25. That concludes the entire document from the initial title to the final email address, adhering strictly to our linear progression protocol. Have we missed any final nuances of the source document structure?
I think we've thoroughly unpacked every definition, theorem, and technical step required. We are ready for the final thought.
This deep dive into Nishio's 2025 paper reveals a profound truth. The p-adic Galois group GRENC harbors abstract symmetries out of Genke that are far beyond the symmetries of the field itself, out of Genke. The gap between the group and the field isn't just present, it's infinitely large.
And the constructed unipitant automorphism, alpha, is that ghost in the machine. It's what ensures that the field automorphisms are not a normal subgroup, creating infinite structural variance. And it is also what breaks these geometrically nice properties, like the Hodge-Tate property.
It's a powerful reminder that in advanced algebra, the group structure contains information that the field structure sometimes fails to regulate, especially in this tricky p2 dyadic case.
We've seen that crystallinity, a hallmark of stability that's derived from geometry, can be instantly destabilized by a purely group-theoretic operation, a simple unipitant shear. And this raises an important question for you, the listener, to consider. What does this extreme instability tell us about the true robustness of p-adic Galois representations? And should mathematicians now focus less on finding stable representations and more on characterizing the unstable space created by additive kink? Welcome back to the Deep Dive. Today we are strapping in for what might be the most structurally dense dive we have ever attempted.
I think you might be right.
Yeah, forget popular history, forget political science. We are venturing into the deepest foundations of mathematics itself. We're confronting a paper from Yu Nishio, and it's all about the fundamental symmetries of number systems, specifically the outer automorphism groups of absolute Galois groups of p-adic local fields.
It's a mouthful.
It is. But our mission, as always, is to take this extreme technicality and turn it into clear, concise, and hopefully unforgettable insight for you. We're going through this paper detail by detail, following the logic of the unabridged protocol, but making sure we deliver conceptual clarity, not just jargon.
And it really is a profound paper. It explores the absolute limits of what we know in p-adic Galois theory. What Nishio shows ultimately is that when the prime p equals 2...
the famous difficult case,
The notoriously difficult dyadic case, yes. The structure of the symmetries governing our numbers is far more chaotic, far more vast than we had previously confirmed. So we're going to trace the argument for how this mathematical chaos is uncovered, linking abstract group theory to very concrete consequences.
I love that framing. Mathematical chaos. Let's start with that intimidating title itself and break down what each piece is asking us to study. So the title is, On the Outer Automorphism, Groups of the Absolute Galois Groups of Two-adic Local Fields.
A lot to unpack.
A lot. Let's start geographically, so to speak, with the two-adic local fields. What kind of number system are we even talking about here?
Okay, so we're working in a really specialized number system. You can think of a local field as a completion of, a familiar number field like the rational numbers, which we write as math BBQ.
Right.
But it's completed with respect to what's called a non-Archimedean absolute value. They are localized systems focusing all the arithmetic attention around the powers of a single prime number.
And since this paper is all about two-adic fields, we're dealing with extensions of math BBQQ sub 2.
Right.
So why is that specific distinction, p equals 2, versus p being some odd prime? Why is that so important in this area of math?
This is maybe the first essential nugget of the entire paper. In number theory, the prime p2, the dyadic case, is almost always the exception. It's the troublemaker.
It's always the weird one.
It's always the weird one. It exhibits vastly different, messier, and much more difficult behavior than the odd primes. And this difference is largely due to the structure of roots of unity.
Oh, yeah.
For odd primes, the group theory associated with p-th roots of unity is relatively straightforward. But when p2, the presence of the primitive fourth root of unity, that's $, the square root of -1, it just complicates the internal structure of the Galois groups so much, particularly a part called the wild inertia subgroup. It makes every proof inherently harder.
So Nishio's big contribution here is bridging a gap that was left open because previous results only worked for those, easier odd primes.
That's it exactly.
Okay, so that sets the stage for the field itself, what the paper calls KK. Next up in the title, the Absolute Galois Group, denoted Nivergy Joller sub K. This group, gal bar gal of K bar over K, this seems fundamental.
It is the abstract object that holds all the secrets. So JBG sub K is the group of all automorphisms of the algebraic closure, which is Double-Gay bar, that fix the base field K.
Okay, let's unpack that a bit.
Imagine your field KK is a universe of numbers. G-Gil-Jal sub K describes all the possible symmetrical transformations of that entire universe that, leave the original landscape completely fixed.
So understanding G-Galois sub K
is equivalent to knowing all the arithmetic properties of the field K. It contains everything.
Wow. Okay, so that brings us to the main object of study, the Outer Automorphism Group, written as out of GK, out of G sub K. Why go through the extra step of looking at this quotient group? Why not just study all the automorphisms out of G Galo to GK Caro?
Because out of G sub K is where the true novelty is. I mean, out of G sub K captures all the symmetries, sure, but many of those symmetries are, in a sense, trivial. They come from something called conjugation, which is essentially just changing your perspective or your basis internally within the group.
It's not a real change then.
It's not a real fundamental change. So by taking the quotient, out of G sub K strips away all these internal trivialities, and it leaves behind only the true, non-trivial, non-intrinsic symmetries of the group.
So if out of G sub K is large, it means the Galois group GK Nalentub K has many more ways to be symmetrical than the field to K itself can actually account for. That's the measure of this chaos you mentioned.
That is the measure of the chaos. And the central mission of this paper is to show that for P2, this group out of G sub K is indeed much larger and much weirder than the small group of symmetries that come directly from the field, which we call out of K.
That is a fantastic roadmap. Okay, that covers the title. We've got the two-adic fields, the Galois groups, and the Outer Automorphism Group. Have we missed any nuances in just framing the problem?
No, I think that's a perfect setup. We've established the core subjects and the central tension. Let's proceed to the data in the abstract.
Right. So the paper is by Yu Nishio, and it's dated December 2025. Now let's move immediately to the abstract, which lays out the two major discoveries.
Okay. The abstract begins by framing the work within a field called anabelian geometry. This is key. Nishio writes, in the present paper, we study the outer automorphism groups of the absolute Galois groups of two-adic local fields from the point of view of anabelian geometry.
Anabelian geometry. It's a concept that's famously associated with Grothendieck and more recently with Mokazuki's work. It asks a really fundamental question, right? Can the arithmetic of a number system be completely reconstructed if you only know its Galois group?
Exactly. In a strictly anabelian setting, the answer is a resounding yes. There's a perfect one-to-one correspondence. But, as the introduction will point out later, local fields are known to be not anabelian in that strict sense.
So the correspondence isn't perfect.
It's not perfect. The field K always has its own symmetries, out of K, and these symmetries map injectively into the group symmetries, out of GK, out of G sub K.
And the second sentence confirms this baseline. Let us recall that it is well known that the natural homomorphism from the automorphism group of a mixed characteristic local field to the outer automorphism group of the absolute Galois group of the given mixed characteristic local field is injective.
And this injectivity is, you could say, the legal basis for the entire paper. It's what allows us to treat the field symmetries, out of K, as a finite subgroup that sits inside the outer symmetries, out of G sub K.
Which sets up the whole problem.
The entire research problem then becomes, okay, what is the size and the behavior of this huge group, out of G sub K, relative to this tiny little subgroup, out of K, sitting inside it?
Okay, so that unpacks those first two sentences. I think we've got the context of anabelian geometry and this crucial injective map. Are we good to proceed?
Yes, that's thoroughly unpacked. Let's go to the next sentence.
The third sentence introduces prior work, which sets the stage for the first main finding. It says, moreover, Hoshi and the author of the present paper proved that for absolutely abelian mixed characteristic local fields with odd residue characteristic P, this subgroup arising from field automorphisms is not normal and has infinitely many distinct conjugates.
Okay, so this is the result for the, quote, easy case when P is odd. The critical concept here is non-normality.
Right. What does it mean for a subgroup to not be normal?
If of K is not a normal subgroup of F among K out of G sub K, it means there's some exotic outer automorphism, let's call it alpha alpha, that when you conjugate alpha K out of K by it...
So you do the operation alpha K, alpha inverse.
Exactly. And when you do that, you don't get alpha K out of K back. You get a completely different subgroup.
That's compelling. So if a symmetry of the big group G del order sub K can fundamentally move the entire set of field symmetries out of K to a new location, well, that implies out of G sub K has to be huge and structurally chaotic.
And the result for odd P wasn't just that it could be moved to one other location. It could be moved to infinitely many distinct locations, infinitely many distinct subgroups. It proved the vastness of out of G sub K in that case.
So that's the prior art. Have we covered that sentence completely?
Yes, the stage is set perfectly. The previous result for odd P is clear.
Okay, so here's Nishio's first main result, addressing that P2 gap. As a result in this direction, one of the main results of the present paper is the assertion that if a p-adic local field satisfies certain conditions, then the set of conjugates of the subgroup is infinite, which thus implies that this subgroup is not normal.
And this is it. This is theorems B and C of the paper, confirmed. It extends that proof of infinite chaos to the hard PT2 case, provided the field satisfies certain conditions.
Conditions which, I assume, guarantee the field has enough complexity to support these weird automorphisms.
Precisely. This confirms that two adic fields are just as profoundly non-anabelian as their odd prime counterparts. The chaos is still there.
So that covers the first thread of the paper, the structural chaos. Does that summary feel complete?
It does. Let's move to the second thread, which is about representation theory.
Right. The abstract references Hoshi's work again. On the other hand, for an odd prime number P, Hoshi proved the existence of an irreducible Hodge-tape p-adic representation and an automorphism such that the representation obtained by pulling back the given representation is not Hodge-tape.
Okay, we have to pause here and give the Hodge-tape property the attention it really deserves.
Please.
So a Galois representation is an algebraic structure. It's a way for our Galois group, GK or sub K, to act linearly on a vector space. Now, the Hodge-tape condition, which comes from a deep area called Penpake-Hodge theory, is like a geometric stamp of approval.
A stamp of approval.
It tells you that the representation behaves well, that it's nice. Usually this is because it originated from an actual algebraic variety, some classical geometric object.
So representations that describe the real geometry of the field are expected to be Hodge-tape. And Hoshi showed that for odd P, you can find an exotic outer automorphism, alpha-alpha, that breaks this.
It breaks it. You take a nice Hodge-tape representation, let's call it a Hodgedal. You apply this automorphism to it, creating a new representation, circ alpha Drito, composed with alpha, and suddenly it's not Hodge-tape anymore. The geometric integrity is shattered.
That is a stunning result. The symmetries of the abstract Galois group can actually distort the geometry itself.
It's the ultimate proof that out of G sub k contains symmetries that are just fundamentally incompatible with the classical arithmetic structure of the field. They are truly alien to it.
So have we fully unpacked the significance of that prior result on Hodge-Tate representations?
I think so. The idea of a symmetry breaking a geometric property is the key takeaway.
And now, Nishio's second main result, Theorem D, closes the gap for He2. As a result, in a direction that is different from the above direction, another main result of the present paper is the existence of a representation and an automorphism that is similar to the above pair in the case where P equals 2, P equals 2.
And there it is. The paper constructs a specific two-dimensional representation over a p-adic field. It's crystalline, which is an even stronger condition than Hodge-Tate, but it is not intrinsically Hodge-Tate.
Meaning
The Hodge-Tate property can be broken by some automorphism. He replicates the entire structure-breaking phenomenon for the P2 case, confirming that P2 is just as chaotic in its action on these geometric representations.
Wow. That's a phenomenal summary of the paper's two main accomplishments. I can really see the deep structural connections now. It seems like the construction of a single, powerful, exotic automorphism alpha is what proves both the structural chaos of out of G sub k and this failure of the Hodge-Tate property.
Precisely. The two main results spring from a single root. The successful and very difficult construction of that one exotic automorphism alpha under the tough P2 conditions.
Okay. That covers the entire abstract. We've outlined the two main threads, non-normality and the Hodge-Tate breaking, both now extended to P-cre2. Have we left any summary points unaddressed?
No, I think we've thoroughly unpacked it. We've highlighted the significance of moving these results from odd P to P2. Let's proceed to the classification and keywords.
Right. Before we jump into the introduction proper, let's briefly note those. The classification is 11S20 Allers 11S2 not, which just confirms the focus is on the Galois theory of local fields. The keywords include mono-anabelian geometry and group of MLF type.
Right, so mono-anabelian geometry is a specific set of tools they use for the reconstruction algorithms. We'll see later how you actually get the additive structure, what we'll call a K plus K plus, back from the abstract group GK of S or U sub K.
And MLF type.
It's just a generic name. It stands for a group of mixed characteristic local field type. It's a way of saying that the arguments hold for any group that is isomorphic to one of these absolute Galois groups. It's about generality.
Okay, let's move into the introduction proper, starting on page 2. This section really reinforces the definitions and establishes the core problem. The first paragraph defines take K as a finite extension of math BBQ sub K, out of K sub K. It defines GK out of DL sub K and out of K dollar sub K, and it confirms that injective homomorphism out of K maps to out of G sub K.
Which, as we said, allows us to treat out of K as a finite subgroup. So out of K S to P out of K is a subgroup of out of G sub K.
This is the essential setup that establishes the central objects of study and that initial inclusion. Have we missed any nuances in that first paragraph?
I think we've thoroughly unpacked it. The injective relationship and the identification of out of K as a subgroup are the key points. Let's proceed to the next paragraph.
Okay, the second paragraph is really the philosophical anchor of the whole paper. It reminds us that for odd P, the equality out GK out of K equals out of G sub K never holds.
Right.
Which means the field is not anabelian in the strict sense, and the main interest of the whole field of study is investigating this difference between odd of K and odd GK out of G sub K.
And that difference is the entire mystery we're trying to solve. The very existence of that difference implies there are symmetries of the Galois group that have no parallel in the field structure itself.
They're truly exotic.
They are.
We've covered the crucial failure of the anabelian property and established the main research question, quantifying that difference. Have we missed any nuances there?
No, I think we've thoroughly unpacked it. This establishes the central motivation for the entire paper. Let's proceed to the next sentence.
The third paragraph brings us right to the research gap. On the other hand, no similar results were known in the case where PP equals 2 equals 2. So the natural question is just how far apart are AK out of K and out of GK out of G sub K in this dyadic case?
And here the paper introduces its strategy for measuring that distance. It's through the reconstructed additive module, which we write as K plus K plus.
Right, this is where mono-anabelian geometry comes in.
Yes, the reconstruction algorithms allow the group out GK out of G sub K to act on this concrete object, K plus K plus.
And this action of out GK out of G sub K on K plus is crucial because it takes a very abstract group relationship and makes it concrete, something you can measure. If an element of out GK out of G sub K acts trivially on K plus, it's probably a boring automorphism if it acts non-trivially.
It's exotic,
Anyway.
exactly, because K plus is a vector space over math BBQ Q sub P. Any non-trivial action on this linear space is mathematically measurable, and it proves that the outer automorphism isn't just some trivial internal conjugation.
Okay, we've established the gap for PQ and introduced the key tool, this action of out of GK, out of G sub K on alt K plus K plus. Has we missed any nuances?
I think we've thoroughly unpacked it, especially the conceptual importance of out GK, out of G sub K acting on the additive structure TA plus delta K plus. Let's proceed to the main results, starting with Theorem A.
This brings us to Theorem A, the main technical result of the paper. It's the proof that an exotic automorphism exists and that it distorts the fundamental structure. The conditions are key here.
Yes. First, the field QK must contain a primitive fourth root of unity.
And second, the extension kilomath BBQ over Q sub 2 must be Galois and abelian.
Right, and those two conditions, what we'll later see as AK gek 2 of 4 sub k greater than or equal to 2 and kilomath BQ 2 sub k over Q sub 2 being abelian, they provide the necessary geometric complexity from the roots of unity and the structural tractability from the abelian base extension to make the subsequent calculations actually feasible.
And the devastating conclusion of Theorem A. Then there exists an outer automorphism, alpha alpha of GK gyro sub k, such that for each non-zero integer n, if one writes alpha plus alpha to the power n sub plus for the action, then alpha plus nact alpha to the power n sub plus, acting on the additive module underlying Q sub 2, is not equal to the additive module underlying Q sub 2.
And this is the definitive proof of exotic behavior. This automorphism, alpha alpha, it actively distorts the base field structure. So math.NT plus Q sub 2 plus is a specific submodule inside of hat K plus K plus. A normal field automorphism must fix the base field, meaning it would have to send GAO Q sub 2 plus Q sub 2 plus to itself.
But this one doesn't.
This one doesn't. The fact that alpha alpha moves elements of the base field module outside of the base field module proves that this alpha alpha cannot possibly originate from a symmetry of the field KIK. It is a genuine group theoretic abnormality.
That's powerful. We have carefully stated and interpreted Theorem A, explaining the conditions and this counterintuitive action on one wath KB2 plus KQ sub 2 plus. Have we missed any nuances?
I think we've thoroughly unpacked the concept of distortion, emphasizing that the outer automorphism fails to respect the structure inherited from math BBQ Q sub 2. Let's proceed to Theorem B.
Right. Theorem B then confirms the structural consequence of this. The set of out of G sub K conjugates of the subgroup out of K utility K is a subgroup of out of G sub K is infinite.
Yes. The distortion we just saw is so severe that it produces this infinite chaos. The existence of that alpha alpha is used directly to show that the normalizer of out of K has infinite index in out EQ out of G sub K.
We've established the infinite conjugacy result, which links right back to the opening discussion in the abstract. Did we miss anything in that connection?
No, I think we've unpacked it. Let's proceed to the formal consequences in Theorem C.
Theorem C simply formalizes this. It says the subgroup out K subtext out K is a subgroup of out of G sub K is not normal.
Which is just the definition of having more than one conjugate.
Right. And there exist infinitely many distinct subgroups of out of G sub K isomorphic to ad chi sub K.
Which is the direct outcome of having an infinite set of conjugates. This just nails down the non-anabelian status for P2. It's the mathematical equivalent of finding a parallel universe for every non-trivial symmetry you apply.
We have covered the structural implications of the infinite conjugates. Have we missed any nuances in Theorem C?
I think we've thoroughly unpacked it. Let's proceed to the representation theory result, Theorem D.
We shift now to Theorem D, the representation breaking result. It says, there exists a finite extension K of math BBQ Shia sub 2, and a continuous representation that is irreducible, abelian, crystalline, but not out-intrinsically Hodge-Tate.
Okay, this confirms the final punchline. Not only is the group structure chaotic, but that chaos has the power to destroy these fundamental geometric properties of the representation ordo-Arun.
And that key term, out-intrinsically Hodge-Tate.
It means that the Hodge-Tate property is stable under all automorphisms of GK Johnny sub K. Nishio proves that the exotic alpha alpha we've been talking about, the one constructed in Theorem A, is the specific symmetry that breaks this stability.
We've established the second major direction, constructing an example where P2 and the Hodge-Tate property fails under an outer automorphism. Have we missed any nuances here?
I think we've thoroughly unpacked it, defining all the properties involved. Let's proceed to the final paragraph of the introduction.
Right. The introduction concludes by noting some related work, particularly by Kondo, who proved similar results for odd p.
Which really highlights Nishio's role as the pioneer for this difficult P2 case.
That finishes the introduction and the summary of major findings. We are ready to move into the notational machinery. Have we missed any connection points before we do?
I think we've thoroughly unpacked it, setting up the logical flow for the proofs, which start with these foundational definitions. Let's proceed to section 0.
Okay, section 0, notational conventions. This section is absolutely essential because it sets up the algebraic environment where this exotic automorphism is actually going to be built.
We have to understand the language of quotient groups to follow the argument.
Starting with topological groups. The first one is d-ab-jol or superscript ab, the abelianization of a group d-di-ja.
So the process of abelianization is really the first step in simplifying a complicated non-abelian group like d-ab-jol or jol or sub k. You quotient out by the closure of the commutator subgroup, which means you're essentially forcing all the elements to commute.
And in this context of Galois groups,
The resulting abelian group, jol or ja o sub k superscript ab, is governed by the beautiful, predictable structure of something called local class field theory. It's the part we understand best.
the notation continues. We have jol or superscript ab minus sensor, which is the torsion subgroup, and then j-ab-jol or superscript ab/joller, which is the torsion free part.
And making this distinction is a very strategic move. Torsion elements are those with finite order. They're generally related to things like roots of unity. The torsion-free elements, on the other hand, often give you structure related to infinite math BBZ sub p extensions.
So by isolating the torsion-free part, dh-joller superscript ab/Cardor.
They can eventually link the group structure to the additive module k plus tof k plus, which is itself torsion-free. That's where the linear algebra proofs are going to happen.
And the last one here is hph sub p, enclosed in parentheses, for the maximal pro-P quotient.
When you're working p-adically, you want to isolate the p part of the group structure. That's the heart of all the complexity in local fields, so you want to focus on it.
That covers the complex notational conventions for groups. Have we missed any nuances here?
I think we've thoroughly unpacked the importance of distinguishing between the torsion and torsion-free parts of the abelianization. Let's proceed to rings.
Okay, under rings. First, we have dollars plus a dollar plus for the underlying additive module of a ring R.
Which we've already seen with k plus, doggle k plus, and dollary qp plus 2 sub p plus.
And second, automorphisms cross for the multiplicative group of units of R.
This distinction is constantly enforced. The automorphisms act differently on the additive and multiplicative structures, and the relationships between them, especially via the logarithm map, are key to the proofs.
Simple notation, but a crucial distinction. Have we missed anything?
No, but you're right. It's a crucial distinction between the additive and multiplicative structure. Let's proceed to modules.
For modules, we encounter this projective limit notation. We have wedge stackrel left arrow. Wedge's Lage is defined as the projective limit over positive integers n of m modulo n times m.
Okay, so the projective limit is how you construct the topological completion of the module. It ensures the resulting object has the necessary topological rigidity to interact with the profinite Galois group GK dog Galabra sub K in a compatible way.
So it moves us into the right kind of topological space.
Yes, into the realm of compact topological groups where the accents are continuous and well-behaved.
That defines the topological completion notation magic double M wedge. And we missed any nuances there.
I think we've thoroughly unpacked it, stressing the role of the projective limit in constructing these topological modules. Let's proceed to fields.
Finally, under fields. The paper just reminds us that a mixed characteristic local field is a field isomorphic to a finite extension of math BBQ sub p.
Which is the type of field our TKK is.
Then we get a breakdown of some really crucial structural invariants. First, to ADD, subset KK, superscript D equals 1, is a subset of K. This is the uniquely determined minimal mixed characteristic local field contained in TK.
You can think of this as the absolute base of the extension. It helps define the crucial parameter TK stackrel TK. D sub K is defined as the degree of the finite extension K over K sub D equals 1.
And is TK D sub K?
This number, TK D sub K, tells us the dimension of the resulting vector space TK plus K plus later on. It's the geometric dimension of the whole arithmetic problem.
Next, we have a.k subset k. OK sub t is a subset of k, the ring of integers, and math.NT subset k OK. The first tracker m sub k is a subset of O sub k. It's maximal ideal.
Standard stuff for number theorists.
And then we define the principal units. 1 plus math frak k botagotek with a preceding small arrow is defined as 1 plus the maximal ideal m sub k.
Okay, in this group, OK kekdal sub k less than is incredibly important. These are the units that are congruent to 1 modulo the maximal ideal. Locally, this group is often isomorphic to the wild inertia subgroup of GK or sub k.
Which you said earlier is the most complex part of the Galois group.
That's where all the action is.
So finally, the paper defines AKO sub k as the largest non-negative integer, such that kk contains a primitive pk root of unity p sub k to the power a sub kth root of unity.
Right, and this value, the highest power of the residue characteristic available as a root of unity, it really determines the local structure of TK relative to math BBQ sub k.
And the condition from theorem A, that kk contains a primitive fourth root of unity, is just saying aak gek 2 a sub k, is greater than or equal to 2 when our prime pk is 2 2s.
Exactly.
We have now established the full machinery of notation necessary for the main proofs. We've covered topological group quotients, field structures, and these crucial topological invariants, ADAD sub k and ADD sub k. Have we missed any foundational details here in section 0?
We've thoroughly unpacked all the definitions. I mean, this lengthy breakdown is essential, as these notations are the absolute building blocks for all the proofs in sections 1 through 4. Let's proceed to section 1 and so on, continuing this detailed conversational breakdown for the rest of the outline.